Good morning everybody. So, today we are going to start or going to discuss heat transfer in different regimes of boiling. So far basically we have seen the dynamics of vapor bubble and mainly the dynamics of vapor bubble on a heated surface. How does the nucleation takes place, how does a bubble grow, and ultimately how does it depart, and what is its effect on the total process of boiling, that we have discussed. So, those discussions are important. Basically they form the groundwork for developing any sort of heat transfer model which is used for the prediction of boiling heat transfer. Now, already I have pointed it out earlier, and this is a very basic thing that we have got in a boiling curve. This is delta T, that means T W minus T saturated, and this side is heat flux. So, in the boiling curve we have got different regimes of boiling. By a heat flux controlled experiment, we will get only the portions shown by the farm line. That means, we will get the nucleate boiling and we will get the film boiling region. Transition boiling we may not be that successful in getting it. So, in the nucleate boiling and film boiling region, what we can find that again there are different regimes of boiling which do not follow the same laws or same mechanism of heat transfer. Like as I have mentioned earlier, we have got isolated region of boiling. Let us say the inception of boiling is at point A to B is the isolated bubble region or partial nucleate boiling region. Then we will have a transition from the partial nucleate boiling region to the region of columns and slugs. Then we will have, let us say this is C, then we will have up to D the fully developed nucleate boiling region, and at D we will have the critical heat flux. D to E is the transition boiling region, and at E we will have inception of film boiling, and the heat flux related to E is known as the minimum heat flux for film boiling. Then E to F we will have radiation. So, basically we can have some sort of models from A to B, then probably the mechanism will be different from B to D. At D people have, this is the critical heat flux region. So, people have postulated different mechanism of heat transfer for the point D. D to E, this region is transition boiling region. I mean, it is till today it is not very definitely, I mean not very well known what is the exact mechanism of heat transfer during the transition boiling regime. So, we do not have many models for the region D to E, but E to F is the film boiling region, and here again models are available. What I mean to say, from engineering point of view, the discussion which we will have today or after this also, in this lecture and later on also, those are very important, because the estimation of heat transfer coefficient is necessary for the analysis of boiling heat transfer, for the design of boiling equipment, for the safety of nuclear reactor system. So, this discussion which we will continue or which we will start today is very relevant. As far as industry is concerned, most of the application of boiling heat transfer will be from the region, will be within the region A to D. That means, within the region of nucleate boiling. So, obviously, people have given more emphasis to nucleate boiling. transition boiling is a very deceptive area, people want to avoid it. So, we will not have much, I mean we will also not do much discussion on this. Point D is very important because it indicates the termination of nucleate boiling. We should discuss it in details. And then E2F film boiling, though we do not desire this mode of boiling in any equipment, in most of the equipment, but some analysis for this is also available and sometimes that may be needed. So, we will start from the isolated bubble region. Now, if I see the modeling approach, or rather if we call it prediction of boiling heat transfer, if we call it prediction of boiling heat transfer, there are two approaches. The first approach is known as mechanistic or phenomenological models. Second approach, correlations. Third one, which is emerging very fast, but still it has to go a long way before it is regularly used for the industrial design, that is your numerical or computational simulation. So, our discussion will be restricted to the first 2 points, that means mechanistic or phenomenological models and correlations. Now, you see mechanistic or phenomenological models are superior in the sense they give us the physics behind the phenomena, and based on the physics only these models are developed, but they have got their limitations also. Like let us put the limitations. Mechanistic models, the limitations are based on simplified assumptions. So, all mechanistic models, any model that will have some sort of a set of assumptions, based on that the models are developed. So, mechanistic models based on simplified assumptions. So, this is one drawback of the mechanistic model, and many cases in the mechanistic model what we do that as we assume certain thing, that simplified assumptions. So, closure is needed. Due to this assumption, all the information from the same model does not come. So, we have to use some other closure relationship, constitutive relationship, so to close the model. I can give some examples, and where we are having difficulty, I can also give those examples. Like you see, for bubble growth or bubbling process, the mechanistic model if we use, then what we are doing, we are assuming the bubble shape. We are assuming the bubble shape to be spherical or to be hemispherical. Okay. But the actual bubble shape could be different. Then we are assuming isolated bubbles, and we are assuming that two bubbles, they will not interact with each other. Two neighboring bubble will not interact with each other. So, this is also assumption which is not valid in actual case. Then let us say regarding the nucleation sites, which is very dependent on the surface, the manufacturing process of surface, the contamination, the scaling process, fouling, etc. So, this is some sort of time varying property of the surface, time varying attribute of the surface, and this is something which is statistical in nature, stochastic in nature. So, by mechanistic modeling, it is also difficult to take care of this type of factors. Then you see that the bubble departure. The bubble departure we analyze based on some sort of force balance, and these forces are static forces acting on the bubble. So, the liquid effect of liquid velocity etc., are not considered in a very rigorous manner. So, you see that assumption is also not fully valid. So, that is why mechanistic model has got their limitation, but even then mechanistic models are done, they are corrected also. Once they are done, these mechanistic models are constructed, they can be compared with experiment, and if we see that there is large discrepancy, then one can correct those mechanistic models. So, these models are done and used, but people also go for correlation kind of prediction. Now, the type of correlations I will discuss, they are not very blind black box kind of correlation. The correlation, again a correlation will be successful if the basic physics is reflected in the correlation. Okay. So, they are based on physical insight. Okay. They are based on physical insight. So, that is why it is not totally black box kind of correlation, and they will have of course empirical constants. Now, as far as the analysis of boiling heat transfer is concerned, we really cannot differentiate between mechanistic model and correlation. We can see more or less a mixed kind of approach, and let us see what are the different models available for boiling heat transfer. The most common, most widely used correlation is due to Rosenow. For nucleate boiling by (1952). He was a professor at MIT. Now, what has been postulated in this correlation is that the process of boiling which takes heat from a heated surface is similar to the convection process. So, if it is similar to the convection process, then so let me write heat transport due to boiling is primarily by convection. So, if this is by convection, then the laws of convection should be applicable to boiling heat transfer also, and then one can define Nusselt number, that is equal to H lambda L by K L or K F, and that is equal to 1 by C S F R e to the power 1 minus n and P R F to the power m. So, let me tell you, by this time probably you have also understood that for liquid either we are using a subscript F or L. So, this is the very well known formula for Nusselt number. So, basic definition of Nusselt number is the convective heat transfer coefficient multiplied by some characteristic length divided by the conductivity of the fluid. This is equal to, I mean, this is dependent on Reynolds number and Prandtl number. So, 1 by CSF is some sort of a coefficient, then Re to the power 1 minus n and Prandtl to the power m, and Prandtl number is defined based on liquid properties, because whenever the basic idea here is we have got a solid surface. In the solid surface we have got cavity. From the cavity a bubble will generate. When this bubble will move, it will create some sort of a convection current. Okay. And the convection relationship is given by this particular formula. Now, problem is PRF, there is no difficulty, we can, depending on liquid property, we can calculate the Prandtl number, but what about Reynolds number? How can we calculate the Reynolds number? So, Reynolds number Re will be some sort of rho and then velocity and then some sort of length parameter by viscosity. So, how this thing can be taken, particularly how can we define the velocity and the length parameter? Already if you see the previous equation, so here for the Nusselt number we have to take a characteristic length. So, probably L could be replaced by that characteristic length lambda L, and this lambda L is what? Physically it is what? Now, people have before constructing this model, people have done number of experiments. Now, what people have seen that the boiling heat transfer really does not depend on the physical dimension. What do I mean to say? That suppose if you take some sort of circular cylinder and on the circular cylinder you have got some sort of boiling heat transfer, you get another circular cylinder of larger diameter. Now, the boiling heat transfer, it is very difficult to get a direct correlationship between the boiling heat transfer and the diameter, or let us say if we take some other dimension of the physical system, it is difficult to get a good correlation between boiling heat transfer and the physical dimension. So, definitely this kind of diameter, or let us say the internal diameter of a tube, that does not become the characteristic length in a boiling heat transfer process. So, it has to do something with the bubbles, because those bubbles are very important for the transport of heat. So, that is why it has been defined like this. Already we are familiar with this kind of expression, sigma by G, rho V or rho G gas and minus rho L or rho F. So, this is how your length parameter is defined. Then u, how the u is defined? U can be defined, the velocity. The velocity can be defined like this. You see, there will be some heat flux given, and depending on the heat flux, more the heat flux, the more will be the heat transfer. So, that means the heat flux has got a direct relationship with the velocity. So, people have tried to use this kind of a relationship, that see this kind of a relationship if you use rho L. So, this gives the velocity of the mass generated due to evaporation. So, more the heat flux, more will be the velocity, and this can be taken as the characteristic velocity for your prediction of boiling. Now, along with this, one can also define H is equal to heat transfer coefficient, that is QW TW minus Tsat. This is again another important point which I need to discuss, that in a boiling experiment, that you can have the wall heated, the wall is at a temperature TW, the bulk of the fluid, this is at a temperature TL. Now, this TL need not be equal to the saturation temperature. TL could be a temperature below the saturation temperature, it could be at the subcooled condition. Now, even then it has been seen that it does not depend much on the degree of subcooling. Rather, if we get a correlation between H and TW minus Tsat for the case of moderate subcooling, it gives a very good correlation. So, that means it is not that much dependent on the actual temperature of the bulk of the fluid, rather it is dependent on the temperature difference TW minus T saturated. So, that is why in boiling curve also we have represented it by TW minus Tsat, and in all the most of the boiling correlations or model, the delta T will be TW minus Tsat. So, you see, this is how we can define basic definition of heat transfer coefficient can be obtained like this. Now, putting all these things together, one can have Cpf or L, that is the liquid side, TW minus Tsat by HFG. This is your latent heat of vaporization. Okay. Again I am telling F represents your liquid and G represents the vapor. So, this is equal to CSF within bracket QW mu F HFG sigma by G into del rho to the power n, this multiplied by mu Cp by K determined at the fluid temperature m plus 1. So, last term you can see this is related to Prandtl number. So, this is how we will get the relationship for your boiling heat transfer. If you see the relationship, you can see that here we are getting a very straightforward relationship between heat flux and the wall superheat TW minus Tsat. So, you can if this relationship is correct and applicable for the range of nucleate boiling. So, part of the boiling curve you can construct with this relationship. Okay. And the unknown quantities what is there in this particular equation is N, M and CSF. So, these three factors are very important, N, M and CSF. Now, N is typically taken as 0.33, N is equal to 0.33, M is equal to 0 for water and 0.7 for other fluids. Generally, for aqueous system and water, M is equal to 0, M is taken equal to 0 and it is 0.7 for other fluids. Then CSF some sort of empirical constant depends on solid fluid combination and also surface condition. Okay. So, there is a very long list how CSF will vary on different solid liquid combination. So, for example, suppose we have got a combination of water and emery polished Cu copper. So, CSF will be your 0.0128 and let us say we have got water and let us say ground and emery polished SS stainless steel. So, CSF will be 0.008. So, you see that there is a range of CSF within which it varies and I mean we will have a list of liquid and solid combination for which CSF is given. So, sometimes you may encounter a liquid solid combination which is not there in the list. So, for that those kind of things, those kind of combinations, it is recommended for other combinations CSF is equal to 0.013. So, basically you will see that the value of CSF varies from okay. So, what has been done that for other fluid, for unknown fluid, a higher value has been predicted. Assuming that for the higher value you will predict a higher heat flux and your design will be on the safer side, but the discretion or the decision depends on you. So, you can take a decision depending on your design application. Okay. So, this is your Rosenow correlation. Rosenow correlation is very famous and very widely used. Even today it is very widely used for many design calculation and it gives reasonably good prediction. What is reasonably good? Probably you will be bit surprised to know that it predicts boiling heat transfer in most of the cases within 100%. In case of boiling heat transfer, this kind of prediction is called good. Boiling heat transfer, so many intricate phenomena are involved and a very accurate prediction is almost impossible. So, 20% or 30% prediction is assumed to be accurate and what I have told for Rosenow correlation 100% within 100% accuracy it is calculating. So, that is called a good or very good prediction. Okay. Now, what is the success? What is the reason of success? This is a good success, whether I mean we may feel bit awkward because we are familiar with much higher accuracy of prediction in other cases, but in case of boiling heat transfer this is a good success and people say that the root of the success lies in CSF. This CSF takes care of many stochastic variables in the process of boiling. That means, there are depending on the surface and the liquid combination, there could be and surface roughness or surface preparation, there could be different nucleation sites, there could be contact angle. The contact angle thing is not directly appearing in your correlation. So, there could be effect of contact angle. So, all these things, this kind of distribution and then contact angle So, all these things are taken care of by CSF. So, actually Rosenow has done a very, I mean with a good foresight he has done this, he has made this correlation, and with the help of CSF there are large number of CSF values tabulated, one can get reasonable prediction of boiling heat transfer. So, now we will go to another correlation of boiling heat transfer. So, that correlation is much similar to your the correlation of Rosenow, but there is some difference. So, that correlation is given by Forster and Zuber almost at the same time, it is in the year of 1954. Now, Forster-Zuber correlation, it assumes that there is a bubble in a superheated bulk of liquid. There is a bubble in the superheated bulk of liquid, and this bubble is small bubble, and the motion of the bubble that creates convection. So, sometimes it is called micro convection model. Okay. The micro convection model, let us say the bubble is growing due to evaporation. So, what will be the mass transfer? What will be the mass flow rate or mass transfer? Mass transfer across the interface. Mass transfer across the interface we will get m dot is equal to Kf TL minus T saturated divided by delta into HFG. Now, this is TL, the temperature of the bulk fluid, and the interface temperature is T saturated. Delta is some sort of a film thickness or boundary layer thickness, and we have already seen by the transient conduction analysis, delta can be scaled like this: pi alpha L, alpha is the thermal diffusivity of the liquid, and T time. So, this is how the delta can be scaled from our transient conduction equation. So, using this basic information, one can write some sort of a relationship like this: d dt of 4/3 pi r cube rho g, that is equal to 4 pi r square m dot. So, basically this is relating the rate of mass transfer and rate of bubble growth. Now, following this logic or refining it, a more accurate solution can be obtained. A rather accurate solution can be may be obtained r dot, that is equal to dr dt, that is equal to root over pi by 2 Kf, the conductivity, thermal conductivity of the liquid, rho g HFG, the density of the vapor and the latent heat of vaporization, then delta T sat by alpha L T. In the above equation, the integration has been done and integration can be done, this above equation can be integrated. So, by integrating and by integrating from r is equal to 0 at t is equal to 0, what we can get, r is equal to 2 root over pi by 2 k f rho g h f g delta t sat So, this is how this form of equation are not very unfamiliar to us. So, we will get how the r is changing. So, bubble radius, some sort of a relationship from bubble growth we will get. Similar relationships we have derived earlier. Now, T sat delta T sat again is given by T w minus T saturation. Once we have got it, let us go back to our generic convection equation. In a convection equation, Nusselt number is given by 0.0015 R e to the power 0.62 PR F to the power 0.33. This is your Reynolds number. Sorry, this is your relationship between Nusselt number, Reynolds number and Prandtl number. Re Reynolds number, that can be approximately told as rho f r. So, what I have taken here, I have taken for the velocity dr dt, I have taken that scale wise the velocity scale is proportional to dr dt, that is what I have assumed, and the length scale I have taken as the radius of the bubble. All right. So, Reynolds number can be estimated by this particular formula. Nusselt number again can be estimated q w delta T sat So, basically it is heat transfer coefficient, the first term, then there is a length scale divided by the conductivity of the fluid. Now, length scale actually has been done in a very typical manner by Forster and Zuber. For the Reynolds number calculation or estimation, we have taken simply r, but for the length scale calculation for Nusselt number, what they have done done some sort of a different methodology, and they got L is equal to delta T saturated rho f Cpf alpha T. This is a lengthy expression HFG, then 2 sigma by delta P and rho f by delta P to the power 1/4. So, this is what they have got for the length scale calculation. Now, delta P term is coming. Delta P is equal to nothing but P saturated at wall temperature minus the P liquid. Okay. So, this is how delta P is calculated. Now, whatever I have done with this, if I now consolidate the formula, so I will get finally the Forster-Zuber relationship is as follows. What is this relationship? See, this relationship is like QW by rho g HFG pi by alpha f to the power half rho f (5 by 8) into mu Cp by Kf to the power 1/3, and R star that is equal to twice sigma by P saturated Tw minus P. Okay. So, this is a very lengthy correlation, but well, it is comparable to the previous correlation which we have got due to Rosenow. There are a few differences. First difference is that here in the Rosenow correlation, if you remember, there was a term called CSF. Now, that term CSF, this is your Rosenow correlation. So, this Rosenow correlation, we had a term CSF, and this term CSF is not determined by some theory, but we have got mainly from experiment, and the CSF values are tabulated or listed for different solid fluid combination. In this case also there is some sort of a numerical constant 0.0015, but this has come from the derivation itself. This is not plugged in from some other source. But again CSF has got some sort of a physical meaning, that it is dependent on the solid liquid combination. It takes care of the wetting property of the solid, like your contact angle. It takes care of the activation site, activated nucleation sites on the solid surface, but in this case it does not have any sort of physical meaning. And in this case the solid characteristics we are ignoring. But even then, due to the functional nature, due to the parameter which are involved in this correlation moderately predicts the boiling heat transfer over a good range for a number of fluids. So, that is the advantage. Now, the problem with this model or the Rosenow model is that this Q is directly proportional to delta T. Now, Q is directly proportional, heat flux is proportional to delta T. This seems very, very logical, but there is one difficulty, that during experiment, as I have already mentioned, that if you provide Q and delta Tw some sort of a relationship, that delta Tw should be Tw minus T saturated, not the actual bulk of the fluid temperature, not the actual temperature of the bulk of the fluid. So, this is one controversy which the engineers or scientists could not resolve very easily. They took time to resolve this thing. This is one of the drawback of this these two correlation. Another drawback of these two correlation is like this. Both of the correlation, they are based on the motion created by the bubble and some sort of convection generated due to this. Now, what happens? There are two bubbles, but in between also there is some fluid, there is some sort of a fluid to solid contact. So, here also there will be some amount of heat transfer. So, this part has not been taken in cognition in these two models. And another thing, what happens that the bubble heat transfer when we think of, so definitely the latent heat or HFG is very important, but at least at the initial stage of the boiling process, again some people have pointed out that the heat transfer due to the transfer of latent heat is only a portion of the total heat transfer. It is not taking care of the entire amount of heat transfer. So, these models, that is why, are not complete models. So, there have been criticism. So, as there is criticism, people have then other models, people have then suggested other models for a better prediction. So, let us see what are the other models possible. Now, the other models, there are many models for nuclear boiling, but the other model which I think will be of some interest to you and it shows a different kind of approach, can be termed as vapor liquid exchange model. Vapor liquid exchange model. The vapor liquid exchange model it is assumed that vapor liquid exchange model, it is assumed that a bubble, let us say there is a bubble, maybe on the wall, maybe just above it. So, this bubble, it is nothing but, this is a bubble, it is nothing but a micro pump. So, when the bubble, let us say the bubble somehow it collapses, or when the bubble leaves this particular surface. So, what it is doing? If it is leaving this particular surface, then it is leaving some sort of a void, or if it is collapsing, it is creating some sort of a void. So, the fluid will rush towards this point, towards the point where the bubble was there. And then let us say the bubble is growing. So, if the bubble is growing, let us say it is growing, so it will push the fluid in the outward direction. So, when the bubble is growing, it is pushing the fluid in the outward direction. When it is departing or collapsing, it is sucking fluids towards its center. And this kind of process keeps on, I mean this growth and departure of the bubble, that keeps on occurring during boiling. So, we will have some sort of a pumping process of liquid due to the motion of the bubble. And this pumping process is mainly responsible for your heat transfer during boiling. So, if this pumping process is responsible for boiling, then how it can be modeled? The modeling mechanism could be, first one has to estimate the liquid flow involved in the pumping process. That is important. And then one has to find out change of temperature of the fluid, and then from there change of enthalpy. So, this change of enthalpy is nothing but what heat is being taken from the wall. So, this is how your heat transfer due to this pumping process can be estimated. Okay. So, I think we will continue it in our next class.